Okay, I want to go through and talk with you about the Work-Energy Theorem, and we'll get to that, what exactly that means, in just a minute. But to start out, let's prove it to ourselves. And the first thing we want to do is review. Let's consider if we're lifting a 10-kilogram bowling ball, we're lifting it from the floor to a height of 2 meters, and we want to know how much work we've done. How much work? So in order to calculate that, work equals force times distance, you remember. And to get the force that we're exerting is equal to the weight of the bowling ball. This is not the force of the bowling ball, it's the mass. So to get the force, the weight, we multiply mass times gravity. That's the force. And multiplied by the distance will get us the work. So plug everything in. That's 10. Gravity is 9.8. And the distance is 2 meters, and you should come out with 196 joules of work. We do 196 joules of work on the bowling ball to lift it from the floor up to a height of 2 meters. Hang on. Now we want to know at this point, now that it's 2 meters up above the floor, how much potential energy does the ball have at that point? Well, we can calculate gravitational potential energy very easily by using the formula mass times gravity times height, mgh. And notice that we actually will come out with the same thing. Mass is 10 kilograms, gravity is 9.8, and the height of the ball is now 2. And indeed, we come out with the same energy. We did 196 joules of work, and the bowling ball now has 196 joules of energy. Based on the answer to those two questions, I think we can conclude this, that work transfers energy. That's the best definition of work that we can give, is that work is a transfer of energy. Work is and we might even want to write this right here on this blank. Work is a transfer of energy. And if we ask the question precisely, where did the energy come from that the bowling ball now has? Well, we can look up here and we can see that since these two numbers are the same, then this energy must have come from this work. So from the work that we did. The point of all of this, the big major league point, is that whenever any amount of potential energy is present in a system, it took an equal amount of work to put it there, because work transfers energy. Work is a transfer of energy. Work transfers energy. Which brings us to the Work-Energy Theorem, which is this: work equals change in energy equals force times distance. You already know that work equals force times distance. Now we're adding this in there because we've just proven to ourselves that work produces a change in energy that's exactly the same amount. So we can say that work also equals a change in energy. And this is going to be an equation that we can use that was much like the impulse momentum theorem that we used right here. This was our impulse momentum theorem. And what we did with this is we would pick things out of it, pick certain pieces out of it to make our own equation based on whatever the problem gave us. And it'll be the same here. We also need to remember that change in energy, just like change in anything else, is going to be calculated by subtracting the initial energy from the final energy. Final energy minus initial energy. All right. So let's look at this problem. If we have a car speeding up from 22 to 44 meters per second, and we're going to pass another car, we want to know how much work was done by the car. Okay, we're dealing with work. If you have work in the problem, you should for sure use this Work-Energy Theorem. So that's what I'm going to start with. I'm just going to write that down. Work equals delta E equals force times distance. And my next question I want to ask myself is, what am I looking for? And in this case, we're looking for the work. okay, which is this right here. So this is what we want. That's definitely going to be a part of the equation that we use. And so we can't use 3 parts. We can only use 2 parts of this equation. So we want to next decide if we're going to use this or this. Okay, and to do that, you go back to the problem and say, okay, well, what did they give me? Well, they give us some speeds, and they give us a mass. They do not give us a force, and they do not give us a distance. So we're not going to be able to use this part of the equation. It's going to have to be delta E. And you might say, well, they didn't give us any energies, so we can't use delta E. No, they didn't. But they gave us what we needed to calculate the energy. Because remember that change in energy is final energy minus initial energy, which is what we said right here. So because of that, we need to know at each of these places what kind of energy is happening at the final and initial states. And since the car is moving in both places, we're going to say that it's kinetic energy both times. And that kinetic energy we're going to say is 1/2 mvi squared, because we're going to use the initial speed for this initial kinetic energy. I'm sorry, that would be the final kinetic energy, my fault. So that would be final speed squared minus 1/2 mvi squared for the initial speed. So final energy minus initial energy, final kinetic energy, initial kinetic energy. Okay, and that will give us how much work is done. Plug in numbers. Mass is 875. The final speed is 44. That's what we're ending up at. And make sure that gets squared. Minus 1/2. Mass is still 875. And the initial speed was 22. And make sure that gets squared. So we have everything we need now. All we have to do is solve all of this stuff. If you calculate this energy, you should get 847,000 minus this energy, which is 211,750. And those subtracted out will give us a work of 635,250 joules, which is our final answer. Alright, so we have to do 635,250 joules of work to go from 22 to 44 meters per second in this 875 kilogram car. Now we're at 44 meters per second, and it says once up to speed, how much work would it take to make the car stop? Okay, so we went from 22 to 44. Now we're going from 44 down to 0. Okay, let's think about that. Let's consider that situation. Once again, write down your work-energy theorem. What are we looking for? Well, how much work? We're looking for work again. So once again, put work in there. Still don't have a force. Still don't have a distance. So we will still use change in energy. So that's final energy minus initial energy. And this time it's kinetic energy, except that since the final energy, since we're stopping, our final energy, we're not going to have any potential energy at this point. We're still on the road. We haven't gone up any height. And our speed is 0. So our final energy here is going to be 0. Final energy will be 0, and we subtract the initial energy from it, which is 1/2 mvi squared. Now the initial energy at this point was the final energy up here. We ended up at 44 meters per second here, and that's where we're starting out for this problem. Okay, so plug in 0 minus 1/2 times 875 times the initial velocity squared, which is 44. You didn't really even have to plug all that stuff in because we just calculated this right up here. Work equals 0 minus 847,000 joules, the same energy that we got before, and you would get a negative 847,000 joules. Now, with work and energy, we're not concerned about negatives really, so it's okay if you just leave this negative off of here and just say that to slow down the car, it takes 847,000 joules to stop. Notice that we had 847,000 joules of kinetic energy when we were going at 44 meters per second. We got rid of all of that energy because we stopped. Our change in energy was 847,000 joules. So to get rid of 847,000 joules of kinetic energy, we have to do 847,000 joules of work. And again, that highlights our work-energy theorem, the first part of which is that work equals the change in energy.